Is a type of unsupervised machine learning in which the algorithm process our data and divide them into clusters. So here when you talk about unsupervised learning, you don't have labeled data, which means your data is unlabeled and you are going to find the trend or clusters inside of it. So you have the raw data and you are trying to group them so that it can make some sense in your application which you are going to use that data. And clustering is a type where you are going to just cluster together based on their similarity. And here in this image I can see, right, these four belongs like a similar group, and we can see the difference here, these belong to a different group. So like that we'll be splitting them into clusters in our clustering algorithm. So when you talk about k-means clustering, it's algorithm which can be helpful for you to perform clustering, and k-means algorithm that can divide the given data into the given number of clusters. So we need to provide the k value here. So based on the k value, the clusters will be differentiated. So if you go for the k value as 4 groups can be splitted, will be given by the algorithm. So if you go with 5 will be given. So how we will find the best value, we'll discuss that later. We have already seen about the elbow plot, remember. Also this algorithm, how it is clustering is, it is based on the centroid based algorithm. So in which the cluster associated with the centroid, the main idea is to reduce the distance between the data point and the respective cluster centroid. So for example, if I am plotting, if I am giving the command the k value as 3, so this will try to fit 3 centroid points, and based on which point, for example, this point is near to this centroid or this centroid, who is nearer, it will be assigned to that value. So if you plot a new point, for example, if I give a new input for prediction, so it will try to fit who is near to that centroid. Based on it, the group will be splitted and they will be clustered in this population. And to find the best k value, the calculation of k value, we use something known as WCSS, which is within cluster sum of squares, which uses this formula, which is summation of xi minus yi the whole square, which is nothing but, so it calculates the optimal number of cluster value. How means this WCSS measures the sum of distance of the observation from their cluster centroids. So it is the sum of the distance, which means, for example, if I have only one centroid in the center here, so what is the distance between all of these each point to this centroid? So it will be very high, right? So all of these points will be drawing their distance from this centroid here, and that will be calculated as the sum of distance, and that will be the WCSS value when you have one centroid, when k value is 1. So this value will be high when you go with k value as 1, because there is only one centroid and all the points will be respected or related to one centroid, and the distance will be really high. Imagine when I increase the k value. So if I go with k value as 2 or k value as 3, if for example let us keep the k value as 10 here. Okay, what will happen is, in most of these places we will be trying to fit the 10 centroids, and the distance, so those who belong to that cluster, their distance will be calculated and summed. So the WCSS value, when you have that number of centroid is high, the WCSS value will decrease because the distance will decrease. The centroid will be much more available near to the point, and that will be the trend. So what we used to do is, to find the best k value, we use as a plot which is elbow method. So what we used to do is, we will be calculating the WCSS value. If k value is 1, what is the value? If k value is 2, what is the value of WCSS? We will be calculating it till k1 to k10, which means for all of these we will get the WCSS value and we will plot it. We can do it with Matplotlib. And with that value, what you can do is, you can find a elbow point. So the elbow point is like a sharp turn, you can see, which looks like an elbow. You can see we have a point here, we have some curvatures here, but it looks like a sharp turn. So you need to find the best elbow point. So which number of clusters providing the elbow point, that will be the optimal number of clusters, and that will be selected for your task. And yeah, so we'll go and see that mall customer dataset once again, that project, and see this elbow point, and let us then skip back into PCA, and I'll be using whiteboard to teach you the math behind it. So without wasting time, we'll first start with that project which I have. I'll show the demo. So I have loaded the customer dataset. So the idea behind this is, I'll show you the dataset with df.head, and see here we are having the customer ID, fine, we are having their gender, their age, and the annual income and spending score. we are not going to particularly predict anything. Okay, so here you can use these features, only these three features, to predict their spending score, like a classification regression problem like that, in your supervised regression problem. But here the main task is to group the customers. You are not going to predict this or that. You are going to find the clusters, so that can be used in data science for targeting their different set of customers and giving their respective offers for them. So with these data, so customer ID is not going to do anything. We'll drop it and we'll get the shape of it. So totally we have 200 rows and 4 columns. We'll get the information about it, and is null.sum, and we can see there is no null value. There is you can see this gender column is having text. We need to encode that too. We'll do that later. And scrolling below, I'm just going to look at the correlations. This is df.corr, and yeah, we are using Seaborn, and we are plotting the heat map. And this is what their correlation details about how one column is related with the other. And we can see some different colors, which purple and blue, which defines that their correlation is here. Okay, so very low correlation and negative correlation is found in these things. And with further visualization, here I am going with the subplot. With dist plot I am plotting, so this is the output we are getting. So we are getting the distribution using the hist plot or dist plot of the spending score, of the age and annual income in your data set. So this is nothing but I am using the subplot. We know, right, the subplot, and then I am passing the title and the dist plot of each columns, and that is what the nice output we are getting. And this is data analysis. We'll go and get the counts, whether they are equally distributed or not. Female is high in the data set, fine. And I'm going to use the label encoder to encode the values. So we'll get the count of it. Yeah, now female is given as 0 and male is given as 1. So who is having the most number, they will be ordered as 1, then 2, in that order, then 3, etc. will be given. Yeah, so now it has been changed, fine. So you can also get the spending score. You can calculate those who all belong to male and those who all belong to female. We are getting their account, and this is the spending score. Male is having the spending score high even though their count is less. And this is a bar plot of, yeah, so you can see the results. Once again, subplots of the gender, their number and their gender, and total spending score as y-axis, and mean spending score, their comparison. Okay, yeah, so that's what we obtained. So we can also look at the relationships between the age and spending score. So with age in x-axis and the spending score in y-axis, we have this. Okay, that is not making any that much sense here. So yeah, we can also find this thing. See here, the age between 20 to 40 is having the spending score high here, and when you cross this age of 45, you can see their spending score. We don't even have any spending score which is greater than 60, which defines that they spend less. This is actually interpretation from the data. And we'll look at the relationship between the annual income and spending score. And when you talk about the trend, we can find a trend here, but we cannot group categories between here. You cannot group. Maybe you can separate this as one and this as one. We cannot find the exact grouping here. But when you plot the annual income versus spending score with, see here, this is just a scatter plot with x-axis is annual income and y-axis is spending score. And here the same x-axis is age and y-axis is spending score, the scatter plot. And what we can see is we can also see the grouping here. So they belong to a cluster, they belong to the cluster, they belong to a different cluster. So here a cluster is available, here a cluster is available. We can see it seems like we can group them into 3 or 5. Mostly if you go with 3, you cannot, you will be biased towards one side. So if you go with 5, that will be good. But we'll consider that, and we can understand these two are important features I have. So I'm going to just take that alone. See here, if I want to take only this annual income and spending score, I can go with df.drop the gender and age column and take that. Or you can also do this task. So what is this giving you? Can you understand this, what this means? Using ilocate, the first thing is the number of rows. I'm going to take all the rows, 200 rows is taken. comma, the number of columns when I am selecting, I am taking the second and third index column. This is 0, 1, 2 and 3. So if I include 0 here, 0, 2, 3, then I'll be having the gender column also. So I'll be taking only the last two columns, and I'm taking the values, which means now if I run this, the X will be array, numpy arrays will be available. So this is just that two columns. Okay, so once I have it, what I'm going to do is, I don't have any Y values here, because we are not going to predict anything, we are just clustering them. So now I need to find the best k value. So for that I'm using from sklearn.cluster, I'll import k means, and you can pass WCSS, and for I in range 1 to 11 I'm passing, and generating a model with n underscore clusters will be the number of cluster values, the k values. I am passing I here, which is going to be first time 1, next time 2, next 3 and so on. And the init method is k means plus plus, and the random state is 42, and I am fitting it. Once I fit it in this k means, in this model, I can get something known as inertia. That will be the WCSS value, which with inertia underscore, and I am appending it to a list, so that by the end I will be getting 10 WCSS values, and I will print that. So I am printing it one by one, so I can see first time this is the WCSS with k value as 1, this is n underscore cluster as 2, this is 3, and you can see the value is also decreasing. You can see the numbers, right? So now if you check the length of this list, it is 10. So I am plotting, okay, between x-axis is range 1 to 11, so which means we'll get from 1 to 10, and y is WCSS. So if I plot it, I'll be getting a graph, and with this I need to find the optimal k value. Where can you find the best elbow point? We also interpreted that 5 could be good. Here also we are having a elbow point, which is you can have confusions between 3 and 5. Here 5 can be optimal elbow point, and we can proceed with that, because you can see furthermore there is not much delay, so they are gradually decreasing. A smooth curve is also available, so this can be plotted as a elbow point. So I am setting the 5 as the n underscore cluster, and going with the same things, and fitting it and predicting it together, and I'm storing it in y. So when I get the values of y, these are my values. So if I go with cluster 5, I can see I'm getting output 0, 1, 2, 3 and 4, which is 5 groups. If I go with cluster as 8, then I should get 0 till 7, which is divided into 8 groups, right? So that is what we have obtained here. So continuing with that, now we have mentioned 8, right? So we have 8 different clusters which you can append, and here the optimal cluster is 5. So I'll go and set it as 5 and proceed with that. And we have this. What is this is for X we have fitted, right, which is 200 rows, and this is what the cluster which is like allotted for all the 200 rows. So first row belong to the fourth cluster, next one belong to the third cluster, like that. And yeah, we'll turn it into a data set or a data frame and visualize it. And what I'm doing here is in df I'm adding a new column, and I'm assigning the value of y there, and I'm getting this output. And I'll go and get the value counts. You can see how many rows or how many people belong to how many clusters. You can find it is not given randomly, it is given based on their relation. You can find this guy and this guy have the same annual income, but they belong to a different cluster, because here the spending score is less, here the spending score is high, and here they belong to the fourth cluster, so their spending score is also less and annual income is also less, in that manner. So now we'll use the count plot and see the distance and difference. So I'll create a dummy variable, once again the count, and now what I'm going to do is, this is my y, right, and you know yx value, which is going to be my features, which is that 2 rows. And what we are doing is, here I'm going to use this plot. So first I'll run this output and tell you how to achieve this visualization. So this is what my output is. Okay, so how am I achieved this much nice visualization which defines each cluster differently? So what I'm trying to do is, see here, my y value will change from 0 to 4, right? So since it has 5 groups, and I'm using a filter. So what I'm doing here is, see here, this is going to be your x-axis value, this is going to be your y-axis value, and my x-axis should be the annual income and y-axis should be the spending score. And where am I having the annual income is in x. In X, this first column is, you can see the data set, which is annual income. Next one is spending score. So this is spending score. Okay, so this belongs to the 0th index. This belongs to the first index. So what I'm going to do is I'm going to use a filter, okay, which is like where y is equal to 0 comma 0. So where it is y is 0. So you can see you will be getting boolean where the value is true. Okay, so yeah, I'll run this. So you need to pass 0 comma 0, which is wherever it is true, you will be getting that value. So I'm using this as a filter, and I'm going to get the x value here. So this is x-axis value. So these are my points. Okay, so what this means is, see here, I'm taking, okay, even though if you pass y equal to 0, you will get wherever it is 0. I'm using 0 comma 0 to use a filter which takes the 0th index of x. So I'm getting the 0th index of x wherever it is 0. Okay, 1 minute. Double equal to, okay, so I have replaced the values. We'll run that once again. Sorry for that. We'll make the prediction once again. Now we have y, we have x. So I'm using the filter to take the 0th index, which is going to be the annual income. This will be the x-axis. So when I go for y-axis, I'm taking the spending score. So for y-axis, I need to take the first index of my x. So this 0 will be common in the x-axis. You can see this 0 will be constant because it is taking the annual income, and this 1 will be constant because it is taking the spending score. And this 0, 1, 2, 3 and 4 represents your y-axis value, which is your prediction or the cluster. So I'm setting some size here, color and the labels. And if you want the cluster centroid, you can get it using k-means dot, so the model dot cluster underscore centers underscore. So if I go and get that, what I'll be having is, I'll be having the number of clusters, they are x and y axis values, x axis value and y axis value. So I am taking that and plotting it for the centroid. So this is what the representation I get. So since I have two features, which is annual income and spending score, I can plot this and see their groupings, right? Imagine you are having another feature, you are considering age also, then it will be a 3D graph. So you want to include another feature, it is 3D, fine. Okay, so now if you want to visualize another more feature, can you plot a row 4D here? No. Can you plot a 5D, or if you have 11 columns, okay, can you plot the 11 features and see it? You cannot visualize that. That is one disadvantage for visualization. Also, consider the features. When you go for algorithms, it is better to go with the reduced features or very minimal features. We have done that in feature selection also. Instead of passing the entire thing, to pass the important one will be best, that is feature selection. But imagine a situation you cannot drop the features, but if you want to take the extract information from it and convert it into a 2 column, for example, if I have 10 columns, if I convert it into a 1 or 2 columns in a 2D, then that will be good, right? It is called as dimensionality curves, which means that when you have multiple dimension means columns here in this sense. So 2 dimension means we are considering annual income and spending score. A 3 dimension here will be annual income, spending score, and another z-axis which will be age or gender. So you can have 4 or multiple dimensions like this. So when you give your algorithm multiple dimensions, it is called as dimensionality curves. So what that means is, when you give multiple dimensions, the algorithm will get confused. So that is the idea behind it. So the more number of columns you are, like for example, you are going to sell your house, and imagine you are going to explain the customer who is going to buy it. And if you explain, like telling him the lot of features, he will be getting confused. This is, for example, you are giving 2-3 houses as example, and you are giving a lot of features. This is yes here, this is no here, this is the advantage here, this is the disadvantage here to all the houses. Then he will get confused to select which house, because he has a lot of options now and he will be getting a lot of confused. So if you go with only simple features or which has the important information, then that will be good. So that's the idea behind here also. So to avoid dimensionality curves, okay, so that will collapse our algorithm, which will decrease its or confuse it. to select important columns, we can go for feature selection or we can go for dimensionality reduction, which is nothing but PCA. So I'm going to show you a glimpse of PCA here. Even though we have two columns, selected two, I'm going to apply PCA here also. So what I'm going to do is, I'll scroll below. So yeah. So PCA is from sklearn.preprocessing import standard scalar, because the PCA algorithm, so what does understands is your data is normal or Gaussian distributed, so you have to scale your values before you go into that. And also you can import from sklearn.decomposition, you can import PCA, and here the number of components will be how many principal components you require or how many important features. So it is not going to select the columns like in feature selection. This is feature extraction, because if you give 10 columns, from that 10 it is going to just take the representation values from it, the importance of it, okay, and convert it into the number of columns you ask. For example, if I ask it to turn into 2, then it will fit and transform and you can see the output. This is my 2 features which are extracted. So how it is done, the math behind it, I'll teach you later. Before that, this is what the output from a PCA looks. If you remember, in day 18 in the project, we had the credit card customer, right, credit card fraud detection data set, which has a lot of columns, but the data they cannot give it publicly, so they have given this feature extracted or PCA values, right? So here if I go with the value 1, we'll see I'm getting the important features in only one column. Okay, so if I go with 4, so I'll be getting 4 different values, okay, 4 columns. So I'll go with 2 here and we'll plot and see it. Here also now I can use this for the k-mean, so I'll select the best using the elbow method. Here also 5 can be good. So if I plot it with that 5, you can get, this is what the PCA transformed value and their group also look like. So how this PCA is actually working, here I have 2 columns, so I can directly go with the k-means. What if I'm having another data set which is having like 10 or 20 columns? What will I do in that case? Okay, so in such cases I cannot use or select a feature selection can be done, or if you don't want to lose information, you can pass that 10 columns and transform it into 2 using PCA. So how it's done, we'll see that now. So talking about PCA, the full form of PCA is Principal Component Analysis or PCA. It is a statistical procedure that allows you to summarize the information content in large data tables by means of small set of summary indices that can be more easily visualized and analyzed. So from my multiple columns, I'm going to take which all important feature I'm just taking it. Okay. So for example, if I tell you, we have already learned about train test split with the exam model, right? For example, like the teacher is giving the question in the training part, and then testing we are writing the test. And feature selection, which is feature extraction, I'll tell you the difference. When in feature selection, what we are doing is we are asking the teacher to give, for example, if I have 10 chapters or 10 columns, I'm asking, I need to focus on only 4 chapters which will be important in the exam. So I'll be learning that 4 chapters and I'll be answering that. But when you go for feature extraction, here what we are doing is we are studying all the 10 chapters, but I'm not studying fully. Okay, the algorithm picks important question from all the chapters and writing the exam. So that's what is feature extraction or PCA does. So for example, if you have a multi-dimension data, you can extract important information and visualize it in 2D if you want, or if you want you can get it in 1D, or if you want you can get in 3D. So we can convert it using PCA. So how it works, we'll see the max intuition behind it in the whiteboard. So I'll be teaching you the max behind it now. So starting about PCA, we want to understand that once again the PCA, what it considers is the data you are going to pass inside is normal distributed. Okay, normal distribution means bell-shaped curve, it is required. So it will be expecting that. So you need to use a standard scalar before passing your data. So once you pass it, okay, before understanding PCA, we also need to understand some more features, which is going to be like what is covariance or what is correlation. So covariance and correlation are two different things. Let us see what is covariance first. So covariance is actually uses a formula. For example, if you want to find the covariance of two things like x comma y, their covariance. So I'll draw it. So the covariance, it uses a formula which is nothing but summation of n to I. So for example, if you have multiple plots, then you can use this formula, which is going to be xi minus x bar the whole square. Sorry, it is multiplied by yi minus y bar and divided by n minus 1, the total count minus 1. So this is the formula for covariance. So what this covariance is telling you is, I'll draw it. So this covariance will give you the relationship between x and y. So what is the relationship between x and y? So the output can be either a positive one, or it's positive or 0 or negative. Okay, so these three things are possible. So what does positive mean? So if x increases and y also increases, okay, how much it is increasing, that we will get in correlation. That is different. We have seen correlation, right? But in covariance, if x increases, y also increases, that is positive value you will be obtaining. If x increases and y decreases, inverse is available, means you will be getting the negative covariance. Or if it is 0, means there is no variance at all, you will be getting. So that is what the covariance is. We will be requiring this later. That's why we are seeing it. And also seeing about the next one. What is then correlation? We have seen about correlation, right? So what is correlation actually? When we talk about correlation, the formula behind this is covariance. You need to find the covariance divided by sigma x multiplied by sigma y. So this is the value for correlation, which means that we have seen, for example, in pandas we have gone with data.corr, right? So what does that give? So it given a table, we can also visualize in the heat map, which will give numerical values, how that particular column is related with this column, how this column is related with the next column. You will be getting their values here. So that is the correlation, which will give you numbers. But here when you go for covariance, that will give you whether it's positive or 0 or negative. That is what only can be obtained when you go with covariance. So that's what their difference. So now, for example, we are going to do a task which is going to be, we are going to convert a 2D into a 1D using PCA. Okay, so I'll explain how it is done. So behind the math, it is using something known as eigenvectors and eigenvalues. Okay, so I'll tell you what it is later, but the final task of PCA, okay, so it will be transforming the values which will be having very high variance. Okay, or who is having the maximum variance. We have seen some variance now, right? So between x and y, so who is having maximum variance or high variance, that will be the principal component. So the principal component can be PC1, which is the first column we got, right? That will be having the high variance. Okay, so if you want a 2D, then you can go and get 2D, which is 2 component, which will be the second component. That will be the variance value which is next to PC1. Okay, so this is high variance which is next to PC1. After that, who is having the high variance, that will be your PC2. So if you want PC3, that will be after PC1 value, which is PC2. After PC2 value, who is having the maximum variance. Okay, so that will be the order. So you can get multiple features from that. So how it is extracting, we'll see that. Now coming back here, we are going to convert a 2D into a 1D. Okay, so once again we'll start with converting 2D to 1D. Okay, so what we are going to do is, see here, so I'm having we are plotting from 2D to 1D, right? So we'll go and draw a 2D. So we have our x and we have our y here, and also I'll be having multiple points here. So what it will do is, now we want to convert it into a 1D. So I'll be drawing a line. So for example, this is a best fit, imagine, and now these are the points which correlate to that, right? So for this point, the value given to this is this one. So this will be your value, which is the transformed value. So like that. Okay, so you will be plotting the lines, and for example, this is how we'll convert 2D to 1D in PCA using the eigenvalues. But how we will find this is the best fit? Once again, in linear regression, we have seen we can have multiple fit. But how will you transform this? Okay, that is a transformed value. You cannot go and interpret it, because that is obtained from a lot of calculations. You cannot go behind and find what is happening there exactly. So how will you find the best fit is which line? Okay, you can have multiple lines like this, which is having a lot of variance. So how we will be finding it? we'll be finding the variance value for that vector, for that line, for all the points that will be calculated, and who is having the maximum variance first. Okay, so that line will be given as a PC1, and the values will be given in the first column. So if you ask the second column or two components, then PC2 will be PC1. After that, who is having the maximum variance, that will be the PC2. The second maximum variance will be given in the PC2. So like that you can get for n number of components. So yeah, so now we can understand that we are actually trying to fit, okay, and transforming it and finding the PC1 value. So PC1 will be a line and PC2 will be another line. So like that, how are we actually achieving that? What is the math behind it? I'll teach you now. So once again, the fit can be, for example, if I draw you, so you can have multiple lines like this, okay, so which can have a lot of variance. Everyone will be having different variance available, straight lines, so they will be plotted. So how are you going to find who is the best fit? So from this, who is having the maximum variance will be PC1. For example, if this line is maximum variance, that is PC1, and for example, if this is having the next maximum variance, that is PC2. And why we are actually taking the variances that defines the relation between x and y, okay. And yeah, so what we are going to do now is to calculate the best or the maximum variance of the fit which is available. So what the PCA is using is, it is using the eigenvectors, and from that we can get the eigenvalues, okay. So what this eigenvalues will be having is the magnitude, okay, or the variance, okay. So if the variance is high, then the eigenvalues will be high and the eigenvectors will be greater, okay. So this is mathematically proven. What we have here is, so if the eigenvectors has the eigenvalues which is high, then automatically that will be the magnitude of the vector, and that will capture the maximum variance. So if variance is high, the eigenvalues will be high, then eigenvectors will also be high. This is max proven. So if we find a way to find the eigenvectors for all the lines which is possible, then we can find the best line which is having maximum eigenvectors. So what is the steps actually in our PCA is, or in finding the eigenvectors and eigenvalues? So if you want to find the eigenvalues, then what is the first step is, what it will perform is, it is find the covariance matrix between the features, okay. So that will be obtained. So I'll teach you how it is done. I'll show you. And the next step is, okay, so we'll be using a formula. For example, consider we are having a matrix which is A, okay, and we are having a vector which is V, and if you perform linear transformation in this, so the output will be lambda and V. So what is this? V is the vector you have passed inside, so that will be obtained. Along with that, you will be getting a lambda value. So what this lambda is? This lambda is nothing but your eigen value. So if you use this formula, you can actually get the eigen value. And what we are doing is, we are using linear transformation, and we want to understand what is linear transformation also. So this is another step, okay. So when you perform this for each line, you will be getting a lot of values. So from that, who is having the greater lambda value, who will be having the greater eigen value, will be having the greater variance. So we'll be selecting the maximum variance from the eigenvalues. So these are actually the steps which is involved in the PCA to find the eigenvalues which is greater. So that will give you the best fit. So once again, when you go the math behind it, so if you want to apply what is linear transformation and what is this A, what is this vector, I'll show you. And before going into that, we'll see what will happen in a linear transformation. So that is a matrix of operation where, for example, if you have a matrix which is P in the shape of M cross N, okay, we'll consider it M cross M, and we are having X which is having the shape of M cross N, and the output, if you perform it, the linear transformation, the output will be Y, that will be in the shape of M cross N only. So for example, if I have a matrix, let us consider P1 up to Pm, okay, and if you go and perform with X, which is going to be x1 is to xn. Okay, and this is the shape of it. So the output will be a matrix which will be like this. So you will be getting the output here, it will be p1 and x1. So till you will be getting till p1 and xn. So like that, here also you will be getting from pm till x1, and the output here will be pm and xn. Okay, that will be the output. This is what happened in a linear transformation. So keeping that in mind, we are going to see about the steps once again of our eigenvalues. So talking about the steps, let us consider once again transforming from 2D to 1D. Okay, so first step, what it is. So if you remember, the first step is calculating the covariance. And for example, if I am having two columns which is x comma y, to calculate the covariance, I know the formula, which is going to be summation of n I equal to 1 xi minus x bar and yi minus y bar divided by n minus 1. And this is the formula. So for example, if you are doing with two columns, then if you perform that, what will be the output for you is, let us consider, let us get the value of a. If you remember, the second formula is a multiplied by the vector, right? So I will show you. For example, if you have a 2 cross 2 matrix, then your output will be like this. You will be having x and y, and plotted in this table, which will be like, here you will be having x and here will be y. So this will be the variance of x, and this is covariance of x comma y, and this is covariance of x comma y, and this is variance of y, right? So once you have it, what you can do is, this is the value of a. So once you have this A matrix, if you remember, the second step is to apply this formula. A multiplied by the vector will be equal to lambda, which is the eigenvalue, multiplied by the same vector. You will be obtaining that back. Okay, so now we have the A, and what will be the vector is, the vector will be from the value or from the line. So previously we have seen, right, we can have multiple fits. So that vector value will be obtained, and if you utilize it and apply in this formula, you will be getting lambda value. So if you go with 1D, if you want to convert into one component, then lambda 1 will be available. If you want two component, then lambda 2 will be available. So lambda 1 is the eigenvalue of PC1, okay, and lambda 2 will be the eigenvalue of PC2. So like that you can get for multiple PC components. So that's what happening behind. So who is having the maximum will be represented as lambda 1. So if you want the second component, then lambda 2, then lambda 3 if you want, so that will be obtained. So for multiple fits, now the best values will be calculated. You can actually visualize this in a website. So I'll show you that website, which is stat.io math visualization, which is interactive matrix visualization. So this is the linear transformer. So I'll go and enable this show input and output vectors. Okay, so the eigenvectors also. So if you remember this is nothing but this is going to be your a value, okay, or point, okay, the values we have calculated, right, the covariance, and this is going to be the vector value, and based on it, this is what your lambda value is. So this is before transformation, and if you apply that transformation, you can find how it is fitted in that line, in which point they are fitted. So you can actually drag and change these values. So if you have a fit here, what will be your output? So that can be obtained by visualizing it, and this is what the matrix multiplication is happening here. There, the linear transformation with your A and your vector will give you an output that will have your lambda value. So who is having the maximum lambda value, that will have the maximum variance, and that will be selected for the output. So that is what happening in PCA. Now we are going to do a project where what we are going to do is, I'll open that. So I'll reconnect this. So we are going to take that music data set, which has a lot of columns, lot of features. We are going to utilize PCA to extract information from that. So here I have a lot of data, which is data and then categorized by artist, by genres, by year. So I'm going to take the main data and let us wait for it to load. So it is about to end. I'll import the required libraries, import pandas as pd, import numpy as np, import matplotlib.pyplot as plt, and import cborn as sns. Fine. So once I have it, I'll load the dataset. The data equal to pd.read_csv, which is data.csv, the name of it. And here we are not going to do the usual thing. You have a different data sets which will be given on the downloadables. You can perform the data visualizations and all. So I'll go over the basic steps here. So I have a data set which is having the music details, which is from Spotify. So we have the valence, the year it is released, the acousticness, who is the artist, the danceability, the duration, energy, and other musical details which is given, popularity, etc. So now we are going to group it. And if you can see, if I check the shape of it with data.shape, I can find my data set is huge, which is 1,70,000 rows and 19 columns. So 19 columns is huge, and yeah, we'll be doing some parts. And before that, you can see, you can proceed with data analytics also. In the year, you can see it is starting from 1921. So it's that very much back. So we'll go with describe. And when I see describe, I can find what's the minimum year, which is 1921, and what's the maximum year, which is 2020. So we have a lot of data, and now I'm going to consider only rows which is having the year greater than 2000. So we'll consider that alone for now to analyze this particular PCA. So I'll get the data which is greater than 2000. So we'll get that songs only. I'll go with the head. So we are having that, and data.shape. Now we have some less number of rows, which is around 39,000. We'll proceed with that. Fine. So we'll go with data.info, and I'm going with PCA. So I'll select the numerical columns alone. We have the Spotify ID, artist name, etc. So we are not going to consider that. We'll drop those and take the numerical features alone. To do that, I can go and do the simple task, which is data.dtypes will give me the data types alone, right? So I can use which is not equal to object, which means the integer and float values from my data will be obtained in this boolean. So I can go and get the columns from data.columns and get that particular columns, and I can pass this also as a filter, right? So you can select this and go with the new data will be this entire thing. Now if I go with data.head, so that will be the output. So these are the features. So now if I go and check the shape, so I have columns which is multi-dimensional, and you can see the dimension is 15. Can you visualize and see the results of 15 dimension? Will it be possible? And also giving these many features, the algorithm will be confused. So you can use your WCSS values and once again do the same thing. But what we'll try to do is we'll try to use the PCA here. So what I'm going to do is I'll import PCA first. Okay, PCA means you need to take from sklearn.decomposition import PCA, and you know, right, we need to scale our values. So from sklearn.preprocessing we'll import standard scaler. Okay, so it's from sklearn import PCA. Fine. So once I have loaded it, I'll go with standard scaler with s equal to standard scaler, and yeah, so the new x value I'll store it as se.fit underscore transform or data, store it in x. Okay, so this is my x, which is having 15 dimension or 15 features. And now what I'm going to do is I'll call the PCA to PCA with n underscore components. We'll set that to 2, and yeah, this is capital PCA, and I'll store x underscore 2d will be equal to PCA dot fit underscore transform my capital X values. This will give me two columns. And you know guys, now what is the first column is your PC1 column, is the first important feature which is having maximum variance. And the next one is that next to PC1 this is PC2. So if you ask 3, so it will give you 3 variance features, and you can see that will represent their importance once again. So that is the transformed values from the eigenvectors, and we are having our 2D. So we'll use this 2D. Now we have two columns like we had in our previous example, that mall customer data set. So now I can go with WCSS will be a empty list, and from sklearn.cluster I can import k-means, and for I in range 1,11 I'll pass k-means will be equal to k-means algorithm. So the n underscore clusters will be I value, and we'll set the random state as 42, and with that I'll go with k-means dot fit our x2d value, and we'll call it to append, right? WCSS dot append k-means dot inertia underscore. So once I have it, what I'm going to do is I can go and plot it, right? So with plt dot plot I can plot between the x-axis is 1,11 and the y-axis will be WCSS. So once that is done, you will be getting this visualization. From that we can find the best n underscore cluster values, and yeah, now we are using the PCA transformed values and passing that and fitting that. From that, in this 2D we are going to plot it, and this is what the values we are getting. And from here I can see the elbow point, which can be good as you can select either 3 or 4. Here we'll go with 3 to get the optimal elbow point. In 4 we don't have that much sharp turns. Here we can select 3, so I'll go with the k-means value as 3. I'll select this. K-means will be the algorithm, and the value of I is 3 now, and we'll fit and predict the values once again here. So I'll store it in y equal to, we'll store it as small y now, y equal to k-means dot fit underscore predict. Yeah. So if you see the y, it will be assigned the 3 cluster values once again, 0, 1 and 2. And now what we'll do is once again we'll plot it with plt dot figure. Okay, that's optional, so we'll go with plt dot scatter. So I need to pass my x values, which is x underscore 2d, and I'll use a filter with y equal to 0, 0. This is x-axis values, and the y-axis I need to get the second, or the PC2, which is going to be y equal to 0, 1, and with that I'll go with color equal to orange, and the label equal to, okay, I haven't completed, cluster 1. Okay, this is a scatter plot, this is for that alone. So now we'll copy all this and create other clusters too, which is going to be here the value of y will be changing, here also the value of y will be changing, and we'll change the color into blue and red, and I'll change the cluster to 2 and 3. This is what the 3 clusters it is plotting, and your x-axis is PC1, y-axis is PC2. We can set that to, we'll also add our centroid, so we can go with plt.scatter. Once again, this will be get obtained from your algorithm, which is k-means dot cluster underscore centers underscore, and I need to get all the thing which is belong to the 0th, which will be the x-axis values, 0th index. If you remember, we got the x and y values, right, 2 index. So the k-means dot cluster centers underscore, and I'll get, and the color will be, we'll set it to brown, and the label will be centroid, and also I'll go with plt dot legend to include the legend, and finally plt dot show. Okay, we have missed this 0, comma 1. That's the issue. Fine. So this is what they are centroids, and this is a transformation from that features which we had 15. We have reduced it till 2, and this is PC1 and PC2. Now you can see the cluster centroids, and it is categorized into 3 clusters. So if you have a new point, you can utilize this, and you can transform it now with PCA and plot it, and with the PC1 and PC2 value where it belongs, that it will be the cluster of it. So this is how we can utilize PCA for dimensionality reduction. And in this session we have also seen about the k-means or elbow method. So that's it about this project. So in the next session we will be discussing or starting with deep learning introduction, and further in the next 10 sessions we will be having introduction about